You think you know how electricity works. You flip a switch, the light comes on. Simple. Electrons flow through the wire like water flowing through a pipe, and boom, you have electricity. That's the story they told you in school. That's the picture you have in your head. And it's completely wrong. Not a little wrong. Not technically inaccurate. Fundamentally, deeply, spectacularly wrong. Electricity doesn't work that way. Not even close. And when you finally understand how it really works, everything you thought you knew about the modern world collapses and rebuilds itself in a much stranger and much more interesting way. Here's the first problem with the story they told you. Electrons are slow. Absurdly slow. When electricity is flowing through a wire in your house, the individual electrons are moving at about 1 millimeter per second. That's not a typo. 1 millimeter per second. A slug crawls across your garden faster than electrons move through a copper wire. If electricity were really about electrons traveling from the switch to the bulb, it would take hours for the light to come on. Days, maybe. But the light comes on instantly, or at least it seems instant. Actually, it takes about a billionth of a second, but that's still incredibly fast compared to the actual electron speed. So, something else is happening here. Something your teachers never told you, because they probably didn't fully understand it themselves. So, what's really happening? If it's not the electrons racing through the wire like you thought, what is it? The answer is going to make you rethink everything. It's not the electrons that carry the energy, it's the fields. Electric and magnetic fields traveling through the space around the wire. The energy doesn't flow through the copper. The energy flows through the empty space around the copper. The wire is just there to guide the fields, to give them a structure to follow. But the energy itself, the thing that makes your bulb light up, never touches the wire. It travels through the air, through the vacuum, through what you think is nothing. And it travels at the speed of light, not at electron speed, at the speed of light, 300 million meters per second through empty space. Think about what this means. When you turn on a light, you're not sending electrons on a journey through your house. You're creating a disturbance in an electromagnetic field that propagates outward at the speed of light. That disturbance travels through the space around the wires, carrying energy with it. When it reaches the bulb, the field interacts with the electrons in the filament, making them jiggle and emit light. The electrons in the wire barely moved. They didn't need to. The field did all the work. You were taught that electricity is about charged particles moving, but electricity is really about fields changing, and fields are as real as particles. More real in a way because fields are everywhere. They fill all of space. Particles are just places where fields do something interesting, where fields concentrate, intensify, create what we call matter. Here's another way to think about it. Imagine a garden hose full of water. You turn on the faucet at one end. Water immediately starts coming out the other end, right? But it's not the same water. The water you let in at the faucet didn't instantly travel the length of the hose. It pushed the water that was already there. The pressure traveled quickly. The water itself barely moved comparatively. Electricity works similarly, except it's not water pressure. It's an electromagnetic field, and it's not confined inside the wire like water is confined in the hose. The field extends outward into the space around the wire, and that's where the energy actually travels. The wire is just the guide. The real action is happening in the empty space around it, the space you thought didn't matter. Now you might be thinking, wait, if energy travels through space, why do we need wires at all? Why not just beam energy through the air without any conductor? Well, actually, you can. That's how radio works. That's how your cell phone works. That's how Wi-Fi works. All these technologies are based on the fact that electromagnetic fields can travel through empty space without any physical medium. But there's a problem. Without wires to guide the fields, the energy spreads out in all directions. It dissipates. It becomes diffuse. If you want to deliver energy efficiently from one point to another, you need something to keep the fields focused, concentrated, traveling in the right direction. That's what wires are for. They don't carry the energy. They channel it. They direct it. They create a structure that the fields follow, like train tracks guiding a car, except the car is made of electromagnetic fields traveling at the speed of light through empty space. And here's the really startling thing. This isn't a new discovery. This isn't exotic physics. This is basic. Electromagnetism, known for over a century. Maxwell's equations, written in the 1860s, describe all of this perfectly. Engineers who design power transmission lines know this. People who build antennas know this. Anyone who works seriously with electromagnetic fields knows that energy flows through space, not through wires. But somehow, when we teach physics in high school, when we teach basic circuits, we tell this simplified story about electrons flowing through wires like water through pipes. And that story is so ingrained, so deeply embedded in the way people think about electricity, that even when you learn the truth later, your brain keeps going back to the old picture. You keep imagining tiny electrons racing through metal, when in reality the metal is just sitting there, vibrating slightly while waves of energy at the speed of light rush through the space around it. Let's make this concrete with an experiment you could actually do. Take two batteries, two long wires, and a light bulb. Put the batteries very far from the bulb. I'm talking kilometers away if you could. Now connect one wire from the positive battery to one side of the bulb, and another wire from the negative battery to the other side of the bulb. You have a giant circuit, thousands of meters of wire. Now connect the batteries. How long does it take for the bulb to light up? If electricity were about electrons traveling through the wire, it would take forever. The electrons would have to crawl kilometers at 1 millimeter per second. You'd be waiting days. But that's not what happens. The bulb lights up almost immediately, in a fraction of a second. Why? Because the energy doesn't travel through the wires. It travels through the space between the wires. When you connect the battery, you create an electric field that propagates outward at the speed of light. That field doesn't get trapped inside the copper. It extends into space. And where there's a changing electric field, there's a magnetic field. Where there's a changing magnetic field, there's an electric field. They feed off each other, propagating through space like waves in a pond. That electromagnetic wave carries energy, and it travels the shortest path between the source and the load, which isn't through the wires. It's through the space between them. The wires just define the geometry, create the structure that tells the fields where to go. But the energy travels through empty space. There's an equation that describes this. It's called the Poynting vector. Sounds technical, but what it tells you is simple and shocking. The energy in an electrical circuit flows perpendicular to the wire, not along it, perpendicular to it. If you have current flowing upward in a wire and an electric field pointing to the right, the energy is flowing horizontally out from the wire into the space around it. The Poynting vector points in the direction of the energy flow, and that direction is always through space, not through the conductor. Electrical engineers know this. They have to know, because when you're designing high-power transmission lines, or antennas or waveguides, you can't ignore the fact that energy is traveling through space. You have to account for the geometry of the empty space around the conductors. But here's what will really bake your brain. The electrons in the wire aren't useless. They have a job, just not the job you think. The electrons move slowly, but as they move, they create a current, and that current creates a magnetic field around the wire. That magnetic field interacts with the electric field to form the electromagnetic field that carries the energy. So the electrons are like fence posts. They're not the thing you're trying to move from one place to another. They're the structure that defines where the real thing, the field, can go. Without the electrons moving in the wire, you wouldn't have the right configuration of fields to transport energy efficiently. But the electrons themselves aren't carrying the energy. They're setting up the conditions for the fields to carry the energy. Let me give you an analogy. Think of a road. Cars drive on the road. The road guides the cars, tells them where to go. But the road isn't moving. The cars are moving. Now imagine the cars are energy, and the road is the electromagnetic field. Except in this analogy, the road isn't solid. It's made of possibilities, of field configurations. And the road extends through empty space, not through solid material. The electrons in the wire are like the painted markings on the road. They define where the road is, but they're not the road, and they're definitely not the cars. The energy, the cars, travels along the structure defined by the fields, the road, through the space around the wire. Here's another thing nobody tells you. When you have alternating current, AC, like what comes out of the wall socket in your house, the electrons don't go anywhere. They oscillate back and forth, 60 times per second in most countries, 50 in others. Forward, backward, forward, backward. The average position of any individual electron is essentially the same all the time. They're just vibrating in place. And yet, massive energy flows through the circuit. How? Because it's not the electrons carrying the energy. It's the oscillating fields. Every time the electrons change direction, the fields change. and those field changes propagate outward at the speed of light, carrying energy with them. The vibration of the electrons creates electromagnetic waves that travel through space. That's electricity, not particles flowing, fields rippling. And this explains something that always seemed mysterious. How can electricity travel through a vacuum, in a cathode ray tube, in a particle accelerator, in the space between electrodes? There are no wires there, no conductors. How do the electrons know where to go? They don't know. The fields know. You create an electric field in the vacuum, and charged particles respond to that field. The field was there first, filling the space, and the particles just follow the field lines. The picture you have in your head is backward. You think particles create fields, but actually fields are primary, particles are secondary. Fields exist everywhere, filling all of space, and particles are just places where fields are doing something particularly intense. So, when you turn on a light, you're not sending particles through wires. You're manipulating fields that were already there, making them oscillate in ways that transport energy from the generator to your bulb through empty space. There's a thought experiment that exposes how deeply strange electricity really is. Imagine two parallel wires stretched across a room, separated by 1 meter. Now, imagine you connect a battery to those wires, but the wires don't touch at the other end. Open circuit. No current can flow because there's no complete path. But here's the question. Is there an electric field between those wires? Yes, absolutely. The battery creates a potential difference, and that difference creates an electric field extending through the space between the wires. Now, does that field just appear instantly? No, it propagates outward from the battery at the speed of light. The information that the battery was connected travels as a wave through space. So here's the strange part. While that field is propagating, while the information is traveling along the wires at the speed of light, there's energy moving through space. Real energy. Measurable. You can calculate how much using the Poynting vector. And here's the shock. That energy is flowing even though no electrons are moving through the wires. Open circuit, no current, but energy flowing through space anyway. How is this possible? Because energy doesn't require current. Energy requires changing fields. And when you connected that battery, you created changing fields. Those changing fields carry energy, and they do it whether or not there's a path for electrons to flow. Now let's make this even stranger. Suppose you close the circuit. You connect the two wires at the other end. Now current can flow. Electrons start moving slowly through the metal, but the energy was already there. The field wave had already traveled through space. What changes when you close the circuit isn't that energy suddenly starts flowing. It's that now there's a continuous path for the fields to reorganize into a steady pattern. The electron current in the wire creates a magnetic field. That magnetic field interacts with the electric field. Together they form a structure that can transport energy continuously from source to load. But the energy is still flowing through space. It always was. Think about coaxial cables, the kind used for cable TV or internet. There's a wire in the center, an insulator around it, and a metal mesh on the outside. Current flows through the center wire in one direction and back through the outer mesh in the opposite direction. But where is the energy? You'd expect it to be in the metal, right? In the conductors, where current is flowing. Wrong. The energy is in the space between the center wire and the outer mesh. In that insulator you thought was just filler material. The equations tell you this explicitly. The Poynting vector points radially inward through the insulator, circling around the center wire. Energy flows through the dielectric, not through the conductors. The conductors just create the fields that guide energy through the insulator. This seems crazy until you realize this is how all high-frequency transmission systems work. Waveguides used in radar systems and telecommunications are literally hollow tubes. No wire in the middle, just an empty metal tube, and yet they carry energy. Gigawatts of power can flow through a waveguide. How? Because the energy is in the fields inside the hollow tube, not in the metal. The metal just reflects the fields, keeps them contained, prevents them from escaping. But the energy travels through the vacuum inside the tube. If you filled the tube with solid metal, you'd destroy its ability to transport energy efficiently. The empty space is where the action happens. And here's something that will really flip your head. Resistors. You know what those are. Components that dissipate energy as heat. You probably imagine resistors work because electrons collide with atoms inside the resistive material, losing energy through friction. That's the standard story. But that's not how energy is actually delivered to the resistor. The energy doesn't travel through the wires to the resistor. The energy travels through the space around the wires and converges on the resistor from all directions. The electromagnetic field carrying the energy flows into the resistor through space, not through the wires attached to it. The wires create the field configuration that directs energy toward the resistor, but the energy itself makes the journey through empty space. You can prove this mathematically. If you calculate the Poynting vector around a simple circuit with a battery, wires, and a resistor, you find that energy flows out from the battery through space, travels along the circuit in the space around the wires, and converges on the resistor from all directions through space. Almost no energy flows through the metal itself. The metal has a different function. Electrons in the metal move in response to the fields. That movement creates new fields that modify the original fields in a way that guides the energy. But the metal isn't the medium through which energy travels. Empty space is the medium. It always was. You were taught wrong from the beginning. And now you can't see electricity the same way ever again. Let's talk about something you use every day without thinking. Your cell phone. When you make a call or send a message, how does the information travel from the cell tower to your phone? There are no wires connecting you to the tower, no cables, nothing physical between you and that antenna miles away. And yet, information flows, data flows, energy flows. How? Through empty space, through air, through what you thought was nothing. The tower creates oscillating electric and magnetic fields. Those fields propagate outward like waves in a pond, except they travel at the speed of light. When those waves reach your phone, the antenna detects the field changes and converts them back into electrical signals. No particles traveled from the tower to you. Just fields, just energy flowing through empty space. This isn't just theory. This is technology you use constantly. Radio, television, Wi-Fi, Bluetooth, GPS, all work on the same principle. Electromagnetic fields carrying energy through space. No wires, no particles traveling, just field waves propagating through vacuum. And here's the wild thing. These waves don't need any medium. In the 19th century, people thought there must be some kind of substance filling space, something that electromagnetic waves could ripple through. They called it the ether. They did elaborate experiments to detect it, never found it. Why? Because it doesn't exist. Electromagnetic fields don't need a medium. They are the medium. They exist on their own, filling all of space, capable of transporting energy through absolute vacuum. Now, think about what this means for wires. When you have current flowing through a wire, you're creating fields around that wire. Those fields extend outward into space. Energy flows through those fields. But the wire isn't special. It's just a convenient tool for creating the right field configuration. You could, in principle, create exactly the same fields without any wire at all. You'd have to do it differently, maybe with antennas or resonant cavities or other tricks, but you could do it. And if you did, energy would flow through space in exactly the same way. The physics would be identical, because the physics is about the fields, not about the conductors. The conductors are just convenient. They make it easy to control where the fields go, but they're not essential. Here's a perfect example. Transformers. You know what those are? Two coils of wire wrapped around an iron core. You put alternating current into one coil, and alternating current comes out of the other. No electrical connection between them. The wires don't touch. So, how does energy get from one coil to the other? Through the magnetic field. The current in the primary coil creates a magnetic field. That magnetic field extends through the iron core and through the space around it. When that magnetic field changes, it creates an electric field in the secondary coil. That electric field drives electrons in the secondary coil. Energy was transferred from one coil to another through space, through fields, with no particles traveling between them. And here's what's really wild about transformers. The energy doesn't travel through the iron core. The iron doesn't conduct the energy. The iron just concentrates the magnetic fields, keeps them contained, makes them stronger. But the energy itself flows through the space around and between the coils. You can prove this by removing the iron core completely. the transformer still works. Not as efficiently because the field's spread out more, but it still works. Energy still flows from one coil to another through empty space. The iron is an enhancement, not a requirement. The fields are the requirement, and fields exist in space, not in material. This tells you something fundamental about the nature of electrical energy. Energy isn't a substance. It's not a fluid. It's not a thing you can hold or point to or touch. Energy is a property of fields, and fields fill all of space. When we say energy flows from one place to another, what we really mean is the configuration of fields in one region is changing in a way that corresponds to the configuration of fields in another region, changing in the opposite way. It's like waves in a pond. The water itself doesn't go anywhere, it just moves up and down. But the pattern of water height moves across the pond. That moving pattern is the wave. Similarly, fields can oscillate in place, but the pattern of those oscillations moves through space. That moving pattern is what we call energy flowing. And here's something that will really bake your brain. When you plug in an appliance, when you connect a toaster or a laptop or anything to the wall socket, where does the energy come from? You think it comes from the power plant through the wires. But the wires don't carry the energy. They just guide the fields. The energy flows through the space around the wires. And here's the really strange part. The energy isn't just traveling from the power plant to your appliance. Energy is constantly flowing in all directions through the space around every wire carrying current. Most of that energy flow is circular. It flows out from one wire and back into the other wire. It doesn't go anywhere. It's just fields oscillating in space, creating patterns of energy flow that don't deliver net energy anywhere. But a small fraction of that energy flow, the part that corresponds to the difference between energy leaving the source and energy being absorbed by the load, that fraction is what we call useful energy. And it also travels through space. So when you look at an electrical circuit, when you see wires connecting things, what you're really seeing is a structure for guiding invisible fields that exist in the space around the wires. The wires are like the banks of a river. They define where the water can go, but they're not the water. The fields are the water, and the fields fill space, flow. Through space, carry energy through space. Everything you thought you knew about electricity was focused on the wrong thing. You were looking at the banks when you should have been looking at the river, and now that you know, you can't stop seeing it. Every time you flip a switch, you're not just sending electrons through metal, you're manipulating invisible fields that extend through the space around you, creating waves of energy that travel at the speed of light through vacuum, delivering power to the devices you use without ever touching a single atom of metal along the way. Now, let me show you something that will completely change the way you think about resistance. You learned that resistance is friction. Electrons collide with atoms in the wire, lose energy, and that energy becomes heat. That's the simplified story. And like most simplified stories about electricity, it completely misses the point. Resistance isn't about collisions. Resistance is about fields not propagating perfectly. When you have a perfect conductor, electrons move in response to fields in a way that creates new fields that perfectly cancel any resistance to flow. It's like synchronized swimmers creating a pattern that flows smoothly through water. But when you have an imperfect conductor, electrons can't respond fast enough or coordinated enough. The fields they create don't cancel perfectly. There's mismatch. And that mismatch means some of the energy in the electromagnetic field is converted into random motion of atoms, heat. But here's the crucial part. The energy that becomes heat wasn't traveling through the wire. It was traveling through the space around the wire. When the wire has resistance, the electromagnetic field in the space around the wire is absorbed by the material. Energy flows from the field into the material, where it dissipates as heat. You can see this mathematically. The pointing vector points inward toward a resistor. Energy is flowing inward through space, converging on the resistor from all directions, being absorbed by the material. The resistor isn't blocking electron flow like a rock blocking a river. The resistor is absorbing energy from the field like a sponge absorbing water. Completely different, completely counterintuitive, and completely correct. Think about what this means for superconductors, materials with zero resistance, no energy loss. You can make current flow in a superconducting loop and it will circulate forever. Why? Not because electrons don't collide with atoms. Electrons still interact with the atomic structure. But in a superconductor, electrons move in a collective, coordinated way that creates fields that propagate without loss. The fields in the space around the superconductor aren't absorbed. They're perfectly reflected back into space. Energy keeps flowing, circulating through the space around the loop, never being absorbed, never being dissipated. And this happens because quantum mechanics forces electrons to move in perfect synchrony. They form what's called a condensate, a state where all electrons act as a single quantum entity. And that entity responds to fields in a way that doesn't dissipate energy. Now, let's talk about something nobody explains adequately: impedance. You've heard the term if you've ever worked with electronics. Impedance is like resistance, but for alternating current. Except it's not really like resistance at all. Resistance dissipates energy. Impedance controls how fields propagate. When you have a capacitor or an inductor in a circuit, they don't dissipate energy. They store energy temporarily in fields and then release it back. A capacitor stores energy in an electric field. An inductor stores energy in a magnetic field. And when you combine capacitors and inductors with resistors, you get complex behaviors where energy oscillates back and forth between different forms of field storage while also being partially dissipated. Impedance tells you how much of this complicated dance is happening. And here's where it gets really interesting. Every wire has impedance, not just resistance, impedance. Because every wire has capacitance, the ability to store electric fields between the wire and everything around it, and inductance, the ability to store magnetic fields around the wire. For direct current DC, this doesn't matter much, but for high-frequency alternating current, it matters enormously. The impedance of a wire determines how high-frequency signals propagate along it, and that impedance is entirely about the fields in the space around the wire. The geometry of that space, what's near the wire, how far the wire is from other conductors, all of this affects impedance, because all of this affects how fields propagate through space. This is why engineers designing high-speed circuits obsess over layout. Not just which components connect to which, but the physical geometry of how everything is arranged, the thickness of traces on the circuit board, the distance between traces, the type of material between traces. All of this matters because all of this affects the fields in space, and the fields in space are what carry the signals. If you place two traces too close together, their fields interact. Energy can leak from one signal to another. Crosstalk. If you make a trace too thin, the fields around it spread differently. Impedance changes. Signals reflect off discontinuities. You lose data, all because you ignored the fact that signals don't travel through the copper traces. They travel through the space around, the traces. There's a reason Ethernet cables, the ones connecting computers to networks, are made of twisted pairs of wires. It's not to keep the wires together, it's to control the fields. When you twist two wires together, the magnetic fields from one wire partially cancel the fields from the other. This reduces electromagnetic radiation from the cable and reduces how much the cable picks up interference from external sources. Why? Because high-speed signals create high-frequency fields, and high-frequency fields radiate energy into surrounding space if you're not careful. By twisting the wires, you manipulate the geometry of the fields so they partially cancel. Less energy escapes, less energy is picked up. Better signal quality. And all of this is about fields in space, not about electrons in metal. The electrons are just the mechanism creating the fields. The fields are what actually matters. Here's one final example that brings everything together: lightning. When lightning strikes the ground, millions of volts, tens of thousands of amperes, massive energy released instantly. How does that energy get from the sky to the ground? There's no wire, no solid conductor, just air. Except when voltage gets high enough, air breaks down. Electrons get ripped off air molecules. A path of ionized plasma forms. That plasma conducts electricity. But here's the thing. The energy doesn't flow through the plasma. The energy flows through the space around the plasma. The lightning channel, that glowing thread of plasma, creates intense fields. And those fields extend outward into the space around the lightning. Energy flows through those fields at the speed of light. The plasma just defines the path, creates the structure the fields follow. But the energy, the massive power of lightning, travels through the empty air around the plasma channel. Just like every other electrical circuit, energy is always in the fields, always in space, never in the particles. So, we come back to the original question. What is electricity really? And now you know the answer you were given in school was completely wrong. Electricity isn't about particles flowing through conductors like water through pipes. Electricity is about electromagnetic fields propagating through space. Conductors don't carry energy, they guide fields. Energy travels through the empty space around conductors at the speed of light. This isn't a technical subtlety. It's not a minor correction to the simplified story. It's a complete rewrite of how reality works. Every electrical device you've ever used, every light you've ever turned on, every appliance you've ever plugged in, works because of invisible fields flowing through space, not because of electrons flowing through metal. And here's why this matters. Because when you understand this, when you really see how electricity works, you realize the entire modern world is built on manipulating fields. Power plants don't generate electrons, they generate oscillating fields. Transmission lines don't transport charged particles hundreds of miles. They guide electromagnetic waves through the space around wires. Your computer doesn't process information by pushing electrons through circuits. It processes information by manipulating fields at nanoscale. The entire infrastructure of civilization, everything that depends on electricity, is really a massive machine for creating, guiding, and controlling invisible electromagnetic fields that fill the space around us. We live immersed in a sea of oscillating fields, and most people have no idea. But there's something even deeper here, something about the nature of reality itself. You were taught to think about the world as made of things, particles, objects, solid matter, and you thought about empty space as absence, as nothing, as the stage where things happen, but not a thing itself. But electromagnetism tells you that picture is completely backward. Space isn't empty. Space is filled with fields, electric fields, magnetic fields, extending throughout the universe, existing at every point in space. And these fields aren't mathematical abstractions. They're physically real. They carry energy, they exert forces, they do things. The particles, the solid objects you think of as primary, are secondary. They're just places where fields do something particularly intense, places where fields concentrate, oscillate in certain ways, create what we experience as matter. And this isn't just true for electromagnetism, it's true for all of physics. Quantum mechanics tells you electrons aren't tiny balls, they're excitations in quantum fields. Quarks, the things that make up protons and neutrons, aren't solid particles. They're ripples in quark quantum fields. Photons, the particles of light, aren't little packets of energy traveling through space. They're excitations in the electromagnetic field. Even space itself, the vacuum, isn't empty. It's a seething sea of quantum fields fluctuating, creating and destroying virtual particle pairs every instant. Reality, at the most fundamental level, isn't made of things. It's made of fields. And everything we experience as solid, everything that seems substantial, is just patterns in those fields. Electricity is your window into seeing this deeper truth, because electricity is where you can actually measure the fields, detect them, manipulate them, use their physical reality to do useful work. When you turn on a light, you're exploiting the fact that fields can transport energy through space. When you use a phone, you're exploiting the fact that fields can oscillate and propagate through vacuum without any medium. When you charge a battery, you're storing energy in electric fields between metal plates. Everything electrical technology does is manipulate fields, and fields are everything. There's nothing else. The conductors, the devices, even the charged particles are just tools for controlling the fields. But the fields are what actually matters. The fields are the underlying reality. Here's the thing that still amazes me after all these years. The speed of light, 300 million meters per second. Why does light travel at that speed? Why not faster or slower? The answer comes from the properties of empty space itself. Space has something called permittivity, which says how easily electric fields can exist in it. And space has something called permeability, which says how easily magnetic fields can exist in it. These two properties, permittivity and permeability, determine how fast electromagnetic waves can propagate through space. And when you plug the numbers into Maxwell's equations, you get exactly the speed of light. The speed of light isn't about light. It's about the structure of space itself. It's about how fast changes in fields can propagate through vacuum. And here's the final kicker. Nothing can travel faster than light, because light is traveling at the maximum speed allowed by the structure of space-time. When you send an electrical signal down a wire, it travels near the speed of light because the energy is propagating through space as an electromagnetic wave, and electromagnetic waves travel at the speed of light. Always, everywhere. Not because there's something special about light, but because there's something fundamental about fields and space and how changes propagate through the structure of reality. The speed of light is the speed of causality. It's how fast cause can lead to effect. It's how fast information can move from one place to another, and it's set by the basic structure of the universe. So, when you think about electricity now, don't think about electrons flowing. Think about fields rippling. Think about energy propagating through space at the maximum speed allowed by the universe. Think about vacuum not as empty, but as filled with fields that can transport energy, transmit forces, do work. Think about conductors, not as pipes carrying electrical current, but as antennas shaping and guiding electromagnetic waves. And think about yourself as living immersed in an invisible ocean of oscillating fields, some natural, some created by technology, all real, all physical, all carrying energy and information through the space around you. You can't see them, you can't touch them, but they're there. They always have been. And now that you know, you'll never look at a light switch the same way again, because you know that when you flip it, you're not simply completing a circuit. You're unleashing a wave of electromagnetic energy that propagates through empty space at the speed of light, carrying power through vacuum until it reaches its destination and makes electrons dance and photons fly. That's electricity. That always was. And it's infinitely stranger and more beautiful than anything they told you in school.